right, well, good afternoon, and welcome to today's research seminar offered by the Center for Transportation Studies here at the University of Minnesota. My name is Linda Prisen, and I'm Director of Research Administration at CTS. And as those of you in the room know, this seminar is being held in conjunction with the CTS Transportation and Infrastructure Council meeting. Just a few items before I introduce our keynote speaker today. And that is, first, you may notice that this webinar or this seminar will be streamed live on the CTS website, so that's why you see the camera in the room here today. And a recorded copy of the seminar will be available after, in approximately a day's time, so we'll record it and then post it to the CTS website. So if you know somebody who wasn't able to be here today who might be interested in this topic, they're welcome to visit the CTS website to learn more about the topic that Mihai will be discussing today. We'd ask you to hold your questions till the end of the presentation, and you'll notice I'm using a microphone, but it's not projecting in the room, and that's because this is our audio to our web live stream, so we'll ask you to use this microphone here in the room if you do have questions about the topic presented today. If you're viewing online, you may type in questions at the end of the seminar, and we'll take a little time to make sure that to see if there are questions from the remote audience as well. So at this time, I would like to introduce our seminar speaker. Professor Mihai Marasteanu is an associate professor in the Department of Civil Engineering here at the university. His major research interests involve applications of fundamental theories to bituminous materials characterization, modeling, and experimental testing. His current research activities include the characterization of low temperature behavior of asphalt binders. We're going to hear about that today, binders and mixtures, and the characterization of asphalt emulsions in relationship to their field performance. Just a quick note before I turn it over to Mihai is that CTS has worked a lot of years with Mihai now, and he's been a great person to be active with in the council and within CTS, so we are happy and just very pleased to have him here today to do our seminar. With that, I'll turn it over to you. Ready to go? Okay, great.
Thank you very much, Linda, and thank you CTS and Terra for the opportunity of presenting our research on low temperature performance of asphalt materials. The title of the presentation is Towards a Low Temperature Performance Specification for Asphalt Mixtures. You notice that I replaced the low temperature. I didn't have enough space, so I thought I could find something that maybe tells you that is about low temperature. And I also wanted to have the title right on top of our very nice civil engineering building. But basically what I would like to do today is to start with a summary of the work that we have performed under two national pool fund studies that have been ongoing back to back now for almost 8 years, and discuss some of the results. But before I move into that area, I would like to actually present a short history of the development of the current performance specification for asphalt binders. This would help you in understanding what we are trying to do with respect to asphalt mixtures, and propose a specification or a draft specification, and discuss what are the steps towards a successful implementation of such a specification. For those of you who probably don't know too much about what's going on in the asphalt area, we have a PG specification, which means performance grade specification, that has been used for the past 2 decades in the United States and actually has been borrowed by many other countries. It is a clever balance between fundamental concepts and level of complexity of test methods and analysis. Basically, it is complex enough to give it credibility, but it is at the same time level of complexity so that it could be easily implemented. And actually it has been, I would say, probably one of the research efforts that has been implemented quite successfully in the asphalt area. This is also described as a purchase specification because it is used to actually buy asphalt binders. So if you want to go in, if you want to select and buy asphalt binders, that's what you have to use, this PG specification. That gives you basically a range of temperatures, 2 numbers. For mixtures, which represent the composite material that is used to make asphalt pavements, and apart from asphalt binders, it has obviously aggregates, coarse and fine, and also filler. There is no parallel effort, or there wasn't any, for many reasons, and I am not going to discuss this. So obviously it is a more difficult to test material. There are other parameters that cannot actually be easily controlled that influence the results. Because of that, when the superpave method actually was proposed, the superpave system was proposed, for a long time there was no mechanical test associated with it. So basically you made mixtures based on volumetric considerations, air voids, asphalt binder content, things like that. Only recently, in the past decade, there were a number of test methods were proposed, and mostly due to the new mechanistic empirical pavement design guide. So it was not a direct material selection type of specification. It was more to provide a test methods that would give you the parameters that were then input into the MEPDG, Mechanistic Empirical Pavement Design Guide, that is currently used to design asphalt pavements. So there was no limiting criteria similar to what we have in asphalts, and in particular for low temperature, there was a test method called indirect tensile test that was used to provide creep, stiffness, and also strength of asphalt mixtures at low temperatures. All right, so let me give you a little bit of a background on this low temperature that we have on asphalt binders. It all started many years ago with research that was done in Canada. Canada has even lower temperatures than we do, so there is no surprise that they were among the first to do that. And this was happening 30, 40 years ago. And basically, they found out that there is a correlation between the mixture stiffness that is measured after 2 hours of loading time and instances of transverse cracking in asphalt pavements. And basically, they had the idea that if you have a material that is stiff, that means that that material is also brittle, which at that time probably was not too far from reality, because we were using plain asphalt binders, no modifiers, no recycled asphalt, no newer technology. So that probably was relatively valid. So if you had high stiffness, automatically that meant brittle material, which most likely will crack. That was extended later on to asphalt binders using an empirical method based on a Van der Poel nomograph. Imagine 30, 40 years ago, the computers were not used, the way we use them today, and we relied a lot on graphical methods. And basically, there were some calculations that correlated the mixture stiffness to binder stiffness, and this is what was used to actually develop the binder specification. So the binder specification looked at the asphalt binder stiffness and correlated it through the mixture stiffness research with low temperature performance. And there is a long discussion here, but anyway, in order for researchers to get this parameter relatively quickly, obviously the team that developed this specification from Penn State University, they came up with a, I would say, very clever way of shortening the test from 2 hours to 60 seconds, basically, and using time temperatures per position, be able to obtain the same results. So basically, they said that 2 hours at this temperature T is equivalent to 60 seconds at the temperature 10 degrees higher. So one point that I would like to make, and it was kind of lost in translation, so to speak, over the years, is that this data, mixture data, was used, but basically it was never published. So actually the only record of any limiting stiffness for asphalt mixtures is mentioned in a discussion during AAPT meeting, I think 1960s, maybe early 1970s. Professor Gene Skow can probably tell you more about that, who is in the audience. And however, that data was never used or published, or, as I said, used to select mixtures. So this is where the current PG specification comes from. And basically, the researchers came up with this limiting number: stiffness at 60 seconds at temperature that is related to the temperature where you build your asphalt pavements should be no higher than 300 megapascals. So if it is higher than 300, that means it's too stiff, that means it's brittle, that means it will crack. So that's how we actually buy asphalt binders today. They also added another parameter that is mostly related to relaxation properties of asphalt binders. Actually, it's a surrogate type of parameter because it is the slope of the creep curve and not relaxation curve. But I'm not going to get into this discussion, but this specification also has another parameter called the M value. And there was a limit on this M value of 0.300. And basically, what this tells you is that if the slope is higher, so it's more than 0.3, most likely your asphalt binder has good relaxation properties. So it's a good viscoelastic material that relaxes stresses. So as it gets colder outside, as it happens, obviously, in winter, this material is not going to actually hold these stresses, so it's going to relax them. So that means it's very good for preventing cracking from occurring, which I guess it's a very good property of asphalt materials that are viscoelastic. So basically, that's where it came from. There was an attempt to include an additional phenomenon called physical hardening, which complicates things quite dramatically at low temperature, which basically reflects the unique properties of not only asphalt but other polymeric materials. And basically what this is if you keep this material at low temperature for longer periods of time, the properties change. So it becomes stiffer and stiffer with time, not just with lower temperature. So at the same temperature, if you test the material after 1 hour, you get a set of values. If you test after 2 hours, those values are going to be different. So there is a stiffening effect. Basically, the structure of the material, depending on how fast you cool it, does not follow the temperature change. So the material changes slower and continues to change even though the temperature does not change anymore. So, but this was another complication, so it was taken out of the specification. So the PG spec doesn't have that for asphalt binders, although it has been proposed in Canada but by our colleague Simon Hesp, and it is used currently in Ontario. Of course, maybe some of you are aware that there is a 10 degrees shift, as I mentioned, 10 degrees Celsius. For example, if you say that a binder has a grade of minus 34 Celsius, the test actually is done at minus 24, so that requirement is for minus 34 plus 10 degrees Celsius. That's how we do it. It's quite unique. If you ask somebody outside the asphalt area, they are going to be completely confused. This was only due to the fact that we wanted to shorten the test time from 2 hours to 60 seconds. In my opinion, maybe it is time that we maybe give up these 10 degrees. As I said, other people have no clue why we're doing that, and maybe try and focus directly on the temperatures, on the parameters that we get at the test temperature that we use today. But I'm not going to get into that discussion. But as you can see, there are deviations from this 10 degrees rule, so not all the binders that are tested at minus 24 will have the same properties at minus 24 minus 10 degrees, which is minus 34, for example. I know it is a bit complicated, but that's how it is right now. So what I'm trying to say here, the current PG spec has a number of limitations, and I'm going to make a point about that. Why is that important? There was also another test, the only fracture test in the binder spec, the direct tension test, developed by my former colleague Raj Dangre, who spent a lot of time. It was the only fracture test, very nice test. However, due to poor repeatability, which, you know, it is the case with fracture type tests, unlike the other ones that were non-destructive, I would say, fracture experiments are by nature less repeatable, and there may have been something associated with the material itself, but this was not explored. And as a matter of fact, our research as part of the first pool fund study that I'm going to mention in a second here found out that exactly the parameters, actually the strain at failure at low temperature, was the one that correlated best with cracking in the field, which really tells you that stiffness is not brittleness. Yes? So you really need a fracture type parameter if you really want to go in a serious way after what makes pavement cracks. And there are replacements to that right now. The direct tension is not actually used, or is used very by very few people. There is another test that is being advertised and used quite successfully by our colleagues at University of Wisconsin-Madison that use a single-edge notch beam, and we are also pursuing another effort in which we used actually a strength test based on beams, but I don't have time to discuss this. All right, so what I'm trying to say is we have a binder specification. It has been in place for 20 years, as I said. This is probably the best implemented, if you ask me, product of the SHARP research effort. Maybe some of you are aware that early 1990s, the federal government actually put $150 million towards pavement research. Unfortunately, after that was finished, there was a big gap with no funding afterwards. So obviously, you always have the issue of continuing funding, and that's the best situation. But anyway, and this PG spec has been accepted, and the fact that the binder is the one that influences low temperature cracking properties has been accepted, I would say, more or less, but most of the people would say low temperature cracking is controlled by the asphalt binder. And actually many studies validated that the current PG specification, with its limitations, actually works relatively well. So if you are in Minnesota, you are going to use a PG binder, an asphalt binder that has the lower range minus 34 Celsius, because you may expect to get temperatures that low. If you move to parts in the southern part of the country, you may end up with minus 22 asphalt binder, because it's not that it's cold down south. So okay, so we had this specification that had some limitations. However, it was really good and was validated by many, as I said, research efforts, and also by what happened in the field. However, the problem actually started when we started to use more asphalt modifiers, and in particular when we started to use recycled asphalt pavement, the new technology, war mix asphalt, this other additive called polyphosphoric acid, or PPA. And all of a sudden, it became sort of difficult to use binder data to predict what mixtures were, because the mixtures all of a sudden were different. I mean, not all of a sudden, but now you started putting other things in the asphalt mixture. So when they are pure mixtures, so to speak, classical mixtures, everything seemed to be working fine. But all of a sudden, you have this issue, and as we use more and more of these materials, I think there is time and there is pressure actually from a number of organizations to come up with a similar performance method for asphalt mixtures. I mean, ultimately, this is what we put down in our asphalt pavements, and it would be nice to have an idea of the quality. Of course, we do, but a better idea of the quality of these materials. So, due to the addition of these new materials, the use of new technologies, asphalt binder testing alone, I can say that it does not provide sufficient reliability to predict low temperature cracking of asphalt mixtures. And this is where the pool fund study, the first pool fund study, actually came into place. It started in late 2003, I believe, and the first phase finished in 2007, actually beginning of 2007, and it was published. And basically, we continue with a second phase that is finishing in the next 3 or 4 months. So what we tried to do here was to basically start a comprehensive investigation of low temperature cracking and look at how binder and mixture may correlate. So can we really use binder to predict mixtures? And in addition, to come up with test methods that could actually measure the low temperature properties of asphalt mixtures that can be used for selecting the right materials and also for input in the mechanistic empirical pavement design guide. So basically, that's what we've done. So we had a lot of money, thanks to our sponsors. There were 4 universities that started working on this pool fund study, and I'm going to acknowledge them at the end. And basically, we took all the different asphalt mixture tests and all the different asphalt binder tests available or that we have been in the process of developing, and try and correlate the results, the parameters coming out of this experimental work in the lab with thermal cracking in the field. And I can tell you this is not an easy thing to do. First of all, you need to have, obviously, a facility where you can monitor pavement performance, and also some sort of organized way of getting the materials used in these projects, the original materials, aged materials, maybe take samples from the road and test them and correlate them with pavement performance. And that's why I think Min Road was very critical in the success of this project, because it's a unique facility that is set up to provide this kind of information. Otherwise, it is very difficult from a logistics point of view to follow, to monitor certain roads, take samples. So this is not as easy. Plus, they also have a very good temperature sensors, which are actually very, very important for asphalt materials. So anyway, we tested, a set of mixtures using these 4 different types of test procedures. Some of them, 3 of them were fracture-based tests. The IDT was indirect tensile test, was actually a strength test, and for asphalt binders, we also used 3 different strength tests. The testing was done on materials prepared in the lab, but we also took cores from pavements selected by our sponsors, various states, that had good and bad pavement performance, and we correlated the results to the performance. So these were, for example, the mixture tests. The first one is called semicircular bend test. It's basically done on a notched specimen. This is the DCT, disc compact tension, again a notch specimen, the classical SEMB, single edge notch beam, that is used for testing many other materials. It's a standard procedure for metals. And also the indirect tensile test, some people call it Brazilian test, that it was used, it's actually has been used traditionally in the asphalt area. So basically you apply compression and you get tensile stresses, horizontal tensile stresses, and you measure indirectly the tensile strength. And you can also do creep tests. So these are some of the test sections that were actually selected for testing in the first pool fund study. And I'm not going to go into the details because I don't have time, but you see we had sections from Illinois, Minnesota, and Wisconsin. And we performed tests that would, at temperatures that would match the low pavement temperature at 50% reliability level according to LTPP. And if you look at some of the numbers here, for Minnesota, this is Min Road facility, that temperature is -24, approximately -24 degrees Celsius, which basically represents a PG asphalt binder of -34 plus 10 degrees Celsius, as I mentioned to you before. So there is some science behind it, so to speak. And we got the results, and then we actually did simple correlations. And we found out that for mixtures, the highest correlation with the occurrence of thermal cracking was observed for fracture type tests, fracture energy, both the SEB and DCT, also fracture toughness, and for asphalt binders, as I mentioned, the strain at failure with the direct tension. And here are some of the plots, and I have to tell you that these plots actually reflect a lot of work. They are not very easy to get, and these type of plots are the only ones so far that can be used to come up with some sort of specification value. If you look at this, on this horizontal axis you have transverse cracks in linear feet per 500 foot sections, and on the vertical axis you have, in this case, a fracture energy obtained with the SEB test. And as you can see here, it appears that, and the correlation is relatively high, that once you get into the 350 or higher, close to 400, transverse cracks actually start to almost disappear. So you have less and less thermal cracks. Yeah? While if you go to lower values, 300 and below, you get a lot of cracking. So this is a good indication that SEB fracture energy may be used for developing a specification, a criterion for asphalt mixture selection. Similarly, for fracture toughness, there is a correlation, maybe not as clear because there are a lot of points here, but we hope with more data that becomes available to perfect these plots. This is DCT. Actually, my colleague at the University of Illinois who developed this plot for DCT, they have additional data from other projects, and they also found out somewhere in the vicinity of 300 to 400. It's probably a limiting, a good value to set up as a threshold for asphalt mixtures. And this is for the asphalt binder. Again, this tells you that basically a higher strain at failure, so more of an indication of a ductile to brittle transition rather than brittle region, would associate with fewer transverse cracks. So that was not a bad finding. So basically, at the end of 4 years of research, we found out that, okay, we developed these fracture tests, and we find out that the results from these fracture tests correlate best with what we see in the field. These results that we used to show those plots were basically performed on cores. So there were cores taken out of the pavement, taken to the lab, and tested. So that is something that we have to keep in mind. The PG spec has done a very good job, and it represents a very good start, but there are other factors that can influence the properties of the mixture. So we really have to have also a test for asphalt mixtures that will give us an indication of the quality of this mix. So at the end of this pool fund study, we are asked by our sponsors to continue the work and come up with a mixture specification. So can we develop that? And we knew that this is a difficult thing to do for many reasons, and I'm going to discuss this towards the end. But we said, we have a lot of very good data, so we would like to move into exploring and hopefully developing a specification for asphalt mixture. So basically, at the end of this current pool fund study, we will provide a concept or a draft for a new mixture low temperature cracking specification. And we will follow the same idea that was basically used for the binder testing, for the binder specification. And that is due to two things. In this way, you have a better understanding, a better correlation between the asphalt binder and the asphalt mixture properties. I have to tell you that for many years, there were two individual groups, the binder guys and the mixture guys, and most of the times they would not communicate with each other. So the binder guys would neglect what the mixture people said and vice versa. So I think it is about time that these two groups get together and come up with a similar way in which they characterize these two materials. And based on the results from the first pool fund study, the research team decided to concentrate in particular on the fracture type tests and in particular on fracture energy. So this is our main goal, to come up with a criterion based on fracture energy, either from DCT or SCB testing, and maybe we will add a fracture toughness limit that is not clear at this point. For a number of reasons, there are some suggestions that the way fracture toughness is calculated is not entirely correct, because these mixtures are viscoelastic and we use linear elastic fracture mechanics. But this is something that I'm not going to discuss here. So basically, focus on fracture energy, use either DCT or SCB. And also, since we have a stiffness criterion for the binder, come up with a stiffness criterion for the mixture. So why not do that? Because this was actually what started this whole thing. And there are various suggestions on how to do that, scenarios. Use the current IDT method that has been used for many years, this indirect tensile test method. Use bending beam rheometer test on thin mixture beams, something that we have been developing for the past 2-3 years. Or even use these fracture tests, but at the beginning of the test, run a creep test with the displacement transducers mounted in various positions. That would allow us to also do a creep measure before we perform a fracture test. The last option would be to take the binder data and use some model such as Hirsch or the model called ENTPE, developed at the University of Lyon in France, as another possibility. So on terms of fracture energy, these are the two tests that actually were further evaluated in this second phase of the pool fund study. You can see that they are quite different. One of them, the SCB, it's a little bit simpler to perform. However, obviously you apply compression and the crack opens in a direction perpendicular to the force, so you have to actually measure the displacement along the force directions, which requires a bit more displacement transducers, while the D-shaped compact tension test, it's a spec test that is used, it's a version of the SENB test, so it's very clear, theoretically quite straightforward, but preparing samples in such a manner drilling holes may actually create some difficulties, although the research team at Illinois, they have done fantastic progress on perfecting that. This is an example for you of the semicircular bend test. And of course, this is, as I said, the fracture test on notch specimens, and the test is controlled, the load is controlled by how fast the crack mouth opening displacement moves, and so we can get a full, also the softening part of the curve. For creep, as I said, we could continue using IDT. However, there are a few issues with the IDT, although so far has done a reasonable job, and this is mostly related to the size effect that is very difficult to quantify if we will ever move into this area, and the failure mechanism actually that may be more due to shear failure than anything else at the top. I believe my colleague at Illinois, they are actually flattening the top of the IDT so they get rid of this problem. This is what we have been proposing for this creep stiffness using these very thin mixture beams, and we actually showed theoretically and experimentally that this can be done, and we obtained similar results in creep for with IDT test. Or use, as I said, binder data with some sort of model. This is just a quick presentation of an so-called analogical model called WIT model, and the expression for creep at the top here, as you can see, there is an expression for creep. It also has an expression for a complex modulus, which is really nice. So once you figure out the model parameters, you can actually also get complex modulus. I'm not going to get into the details. And basically, it can be shown that the creep stiffness of the mixture is directly related to the creep stiffness of the binder using some parameters that can be obtained for experimental work, which is actually quite important. And this transformation, as we call it, it's very easy to also apply backwards. So to basically solve the inverse problem, in which if you know the asphalt mixture property, in this case the creep stiffness, and you get the binder property, which is very important when dealing with mixtures that contain wrap, because this is a way in which you can find out what the properties of the asphalt binder, the contribution of the asphalt binder in the mixture is. So this is work under investigation, but this was very nice work, and we have been using it. Okay, so after all these discussions, so what are we proposing? And of course, this is very preliminary. We still have a few more months to finish the project and get a little bit more data, but based on the information we have right now, most likely a lower limit of 300 to 400 joules per meter squared appears a reasonable value for fracture energy, either with SCB or DCT. And this is a value that you get at PG plus 10. In most cases, will match this LTPP database temperature. And as I mentioned, is obtained on extensive data from University of Illinois and University of Minnesota. For fracture toughness, I can't say exactly if we are going to have this, possibly maybe a value of 800 kilopascal, but this is debatable. I mean, are we going to put a lower limit? So of course we would like higher toughness and higher energy if possible, but sometimes they go, as you well know, in opposite directions. And for those of you who are not familiar, this is the type of information we get from fracture tests, SCB or DCT. And this is the curve that also has the softening part, yes, which is very important in modeling crack propagation. And basically the energy is the area under this curve, and the fracture toughness is related to the peak load. So you know where that comes from. Here I show some results of fracture energy obtained on different types of mixtures that we tested as part of the second phase of the pool fund study. And as you can see, we have values between 200 and 800. Of course, you will see here immediately the huge temperature effect on properties of asphalt mixtures, including fracture. As I mentioned before, asphalt mixtures, even at this low temperature, they still have a strong temperature component, so they are quite significantly affected by temperature. So obviously we are interested in having some values that are above 400 and 3 to 400, and as you can see, all the mixture tested here seem to be in that area. So basically a very good job with these mixtures. Same thing with SEB, so we can see that the values are similar. So the mixtures that we tested were actually good mixtures. So that would be a number that we could propose as a threshold for selecting asphalt mixtures. For creep stiffness, this is something that we are still investigating. Basically what we've done more out of curiosity was to take the binder 300 megapascal limiting value and convert it to an asphalt mixture limiting value. This is a bit tricky because in asphalt materials you also have a very important factor called aging, and without getting into the details, the binder specification is done on the binder after long-term aging called PAV, pressure aging vessel, and the mixture testing, most of mixture testing is done after short-term aging. There is a long-term aging procedure, but some people don't think it is appropriate or really simulates what happens in the field, which is a different thing that has to be mentioned here. For this slope, it may be very difficult to place a limit because the stiffness of mixtures is very high and the creep stiffness curve is very flat. So we have very, very small m values, which makes any sort of threshold value, I would say, difficult to interpret, as you may have actually some errors in your test method that can be higher than significant, differences in this in the slope. All right, so this is not the only thing that we are going to do. So don't think that we spend all this money just to come up with these parameters, which it was a huge effort. Most of these parameters will also go into the MEPDG, the thermal cracking model component of it, the low temperature cracking model. Currently we have something called TC model, and our colleagues who developed the TC model, they actually will provide, I believe, very soon, a new version of the TC model called Ely Crack, Ely from Illinois. And of course, I couldn't resist not to ask them if the best coffee in the world, Ely, is also made in Illinois. So I know that it's not made there, but anyway, just wanted to make a joke on them. And you can actually use these parameters from testing as input in this thermal cracking model that I think they are going to provide as a separate standalone code that can be used, as I said, by itself or in conjunction with the MEPDG. So basically, in the new thermal cracking model, you will need creep properties of mixture, fracture energy of mixture, which was not used before, thermal coefficient of thermal expansion, contraction, pavement structure information, and obviously input about the temperature of the location. The output, the thermal crack spacing versus time, or number of thermal cracks per 500 feet of a test section. So basically this is what is expected. So you input all these values and it will tell you after this many years your pavement is going to be cracked like crazy, or if you use this type of materials, or it's not going to crack for many years to come, which we all want. So basically that's what we are proposing in at the end of this second pool fund study and last pool fund study. So there are a number of main obstacles which are, I would say, more related to mixtures in general. It has nothing to do with low temperature properties. And this is also a reason why we didn't have a mix specification, because there are, as I said, a lot of additional factors that influence properties. Unlike the asphalt binder, you know, that's the asphalt binder. Is basically, we consider it a homogeneous material. We know its condition, we put it in a rheometer and we test it and we get consistent numbers. But now you get this composite material, and one of the main issues is how are you going to prepare your mixture? And there are actually research going on trying to come up with an answer. Because you can do it in various ways. You can basically take loose mix from the mixing plant. So you go at the mixing plant when they are making this nice asphalt mixture, you know, fresh from the hot mix plant, and take it to the lab and prepare your specimens. You can select it behind the paver, take loose mix. This is done, you know, on a regular basis. You can even take cores from a newly built pavement, although that is always an issue. I mean, you build a nice new pavement and then you go there and take cores out of it, but I guess it's maybe for a good cause. Prepare your specimens from scratch. So you have the mix design, you take the aggregates, you know, you look at the mix design, you take the right aggregates, the proportions, the asphalt binder, you heat it up, you compact it in the lab, prepare specimens. Then, of course, how do you prepare the specimen? How do you compact it? Gyratory or slab? Obviously, gyratory is the most widely used, but some people say, well, gyratory doesn't really represent field conditions. Okay, so that's another big question, and nobody has a good answer for that. In terms of air voids, how am I going to compact it to 4%, that is the mixed design, or 7%, that is the most likely value for the pavement out there in the field? And obviously many people are suggesting 7% because it's more representative of what is out there. Yes, we are not going to get to 4%. Then another big factor that again is not well understood, aging. So are you going to short-term age it, which is representative of what happens to the mixture after it comes out from the mixing plant, is laid down and compacted, or long-term, which means the aged mix after 5-7 years in the pavement. And of course the issue is the laboratory procedure for long-term aging representative of the field? And if you talk to the chemists in the area, they'll tell you a lot of things, you know, and it gets quite complicated. So many ifs, many obstacles. What we will suggest is, look, let's come up with a set of mixture preparation and aging condition. So we will start somewhere. I mean, the PG binder that seemed to do a good job was not perfect. Yep. So why don't we start somewhere? And as we get more data available, we will maybe provide correlations that would take into account aging, sample preparation, and things like that. So we believe that it is time to move on and finish this project and implement a low temperature mixture specification. We are not going to implement it, but we are going to provide all the help and support that we can. And try it, and even if it's not perfect, so at least we start somewhere. So that is what we would like to do once we finish or at the end of this research project. Okay, before I finish, I would like to provide some acknowledgments. And I'm showing here a picture from August 2003, the initial meeting at the University of Minnesota. I guess there are a lot more people interested in low temperature cracking at that time. Maybe they were hopeful and that we were going to be able to solve it very quickly, which actually it's not possible because it is a difficult problem. But I would like to mention that this work would have not been possible without the generous financial and logistical support from MnDOT, which was also or is the lead state. They have obviously provided the samples that we have tested in the lab, taking cores from MnRoad, loose mix, and without this help, obviously we wouldn't have been able to generate all this interesting data. And of course, the support from all the other states that participated: Wisconsin, New York State, Connecticut, Iowa, North Dakota, and the consistent supporter of this project, and of course Federal Highway Administration. I would also like to acknowledge the critical contributions of our colleagues from University of Wisconsin, University of Illinois, and Iowa State, and to thank them for the great teamwork. And with this, I would like to conclude and ask for questions.
Thank you, Mihai. And Joe's going to come around with the microphone in case somebody has a question for Mihai on the results of this research. Because of we're broadcasting on the website, we'll ask you to use it. Yeah. Thanks, Gene.
Hello, my name is Gene Skoke. I'm sorry I was late. But anyhow, I thought one thing you might want to do is define MEPDG. And that's a mechanistic empirical pavement design guide, which well, a number of people here have been involved with and all that. So, but also I think a very important thing is like you say, getting the mix involved. When the PG grading first came out, everything was based on the asphalt, and most of us old people said, well, it's a heck of a lot more than the asphalt. It's how well you design the mix and things like that. And so I think this is a fantastic project in which trying to get all those things put together into a mix. And so I think looking at how this varies with time will be very important and such. So
that's a very good point.
Questions, but we'll deal with that later.
Thank you, Gene. Yes, you are absolutely right. I guess the way to solve this problem is to continue monitoring pavements and take samples out of the pavement and test and see how they change with time. Although, as you know, this means that there has to be a long-term commitment to such type of activity, and funding and long-term commitment is kind of difficult to achieve these days, but you are absolutely right. Yep.
Additional questions?
One other thing is we had a project called 183, which some people here may know about, and others not. But that was an old project that started back in 1963. And after about a year and a half, the materials engineer of the highway department said, well, haven't you done enough of this now? What are the results? And so it's the same old thing of you design a pavement for 20 years, and then you want to find out whether it's good or bad in 1 or 2 years. So I think it's a long-term commitment, like you say. So
I agree.
And I had a question also about implementation, because I'm assuming that when you come out with this specification proposed, that state by state it will be sort of considered in terms of their implementing it. And I wonder if you could talk a little bit about that process, and then also, do you feel like you're getting to the right venues to do outreach, like TRB and potentially AASHTO, to be able to spread the word about the results and get these sort of northern climate states to get on board to potentially adopt it?
That's a very good question. Obviously, you can do the greatest research. If it's not advertised correctly, nobody knows about it. I think our main venue was actually through Federal Highway Administration expert task groups. I am a member of the binder task group, but I also made presentation at the asphalt mixture. And basically, at these meetings, you propose various things. They are discussed by the group and also the attendees that come from, you know, all USA. And at the end of the discussions that may take maybe a couple of meetings or maybe a couple of years, then the ETG sends it to AASHTO for a draft method first and for a ballot. And that was our actually main venue for doing this. Of course, we presented the work, and not just me. I mean, this is not just my work. My colleagues at the other universities, they have also presented their research results. And I think there is a lot of people actually have been asking for some sort of specification on asphalt mixture low temperature. There has been a lot of focus on the high temperature with rutting. But now, as we start, as I said, using more RAP, war mix asphalt, that is a fantastic technology, we may actually have to provide a better way to characterize low temperature properties. So I think at the national level, there is a lot of awareness. Now, in terms of implementing it, that is something that probably it's out of our hands, but we hope that this will be done in the future. So,
I had just one more question, Mihai, because I know you've been doing some work internationally as well to collaborate with a colleague in France. And if you could talk a little bit about that, as well as maybe some applications or interests that might be occurring internationally.
Yes, actually, we have collaborated with a number of people. With my colleague in France, was mostly using this ENTPE transformation, and also looking at a unique way that they developed to improve low temperature cracking properties by using ultrafines. And we have also collaborated with a colleague from Spain that have been implementing their own test method for fracture of asphalt mixtures. But I think a lot of research groups in Europe are moving into the same direction with fracture. So the group at Delft has done a number of tests using fracture methods, and other people as well, also our colleagues in Italy. So we have been actually collaborating with many people, and also my colleagues through this project have a lot of collaboration. So we think that a mixture specification will probably help everybody. And I know that in Europe they have, for example, a standardized methods for all the countries in the European community, and they are moving into a similar direction. So we'll see if they're going to beat us or to it, or we're going to be the first ones to implement it. So,
any additional questions for Mihai? All right. Well, please join me in thanking him for the seminar today.
Thank you.
Thank you. And before we end, I just did want to acknowledge the co-sponsorship of the Transportation and Engineering Road Research Alliance, or TERA, of this seminar. So they were a co-sponsor with CTS for the seminar today. I wanted to also acknowledge that we have forms documenting professional development hour earned today for your attendance in your meeting packets for those of you here who are here in the audience. And hope you'll stay for the meeting. At this point, we'll sign off from our web seminar, and we'll continue with our meeting here today. Thank you.